For the following section 1.3, we're going to be talking about radicals. Radicals are another word for things like square roots and cube roots. To start off with, we'll introduce some definitions and facts. The first being that if b squared is equal to a, then b is a square root of a. So if you can take some number and multiply it to itself to get another number a, then that number b that you multiplied to itself, or you squared, is a square root of a. So for instance, if we take 5 and square it, we get 25. So 5 is a square root of 25. But also if we take negative 5 and square it, we again get 25, because negative times a negative is always a positive. So, negative 5 is also a square root of 25. So when we talk about square roots, we're typically referring to the positive square root or the principal square root. When we say find the square root, we're typically saying we're dealing with the positive one. It's not as common to refer to the negative square root when you say to find a square root. But from here, like I mentioned earlier, this section is about radicals, not just about square roots and cube roots. So this symbol does not mean the square root. This is what we call the radical sign. And in particular, when you put some number here in the top left, I've put an n to show that it can be any number, any whole number technically, but when you put a number here, that's the radical's index. That tells you how many of the same factor you need to simplify this. With a square root, there is technically a 2 here, but we don't write it there because it's not simplified. But that's really the radical index, a 2. With a cube root, there's a 3. With a fourth root, there's a 4, and so on. And that tells us how many of the same factor we need to simplify the radical. So, to explain that in a little bit more detail, our process to simplify a radical, which we write the nth root of x, we say that to find the simplification of the nth root of x, we are going to find the prime factorization of x first. So we're going to break up x into all of its prime factors. Prime factors are numbers that can only be divided by 1 in themselves. And once we do that, for every n like factors, we are going to cancel them out inside of the root, or the radical, and multiply one of them to the outside. So whatever radical index we have, if it's a square root and it's a 2, or a cube root and it's a 3, then we are going to look for that many of the same number multiplied together inside of the radical, and that tells us how many we need to cancel inside of it to multiply 1 to the outside. And from there, once we've done that, we will simplify, and we're done. Alright, now that sounds really complicated, but it's something that you've probably done before getting into this class. So, we have the square root of 196. Let's go ahead and simplify that using this process. So the first step is to find the prime factorization of 196. There are a lot of ways to do this, factor trees, box method, and so on, but the most common method is probably factor trees, which is what we'll use. So, we need to take this 196 and find two numbers that multiply to give us 196. Since it ends in an even number, that means it's automatically divisible by 2. If it ends in a 0, 2, 4, 6, or 8, it's going to be divisible by 2. And if we divide 196 by this 2, we'll get 98. When we're doing the factor tree, every time we get a prime number, we're going to circle it. So we know to stop using that branch and to just continue on with another branch that isn't finished. So 98, for instance, we can break down into 2 and 49. Again, circling the 2. And 49 we can break down into 7 and 7. Circling each of the 7s because they are both prime. And this gives us our prime factorization. 196 is the same thing as 2 times 2 times 7 times 7. And now, because we're finding a square root for every 2 of the same factor, we will cancel them out and multiply one of them to the outside. And then again, we have 2 7s, so we will cancel the 7s out and multiply one of them to the outside. And when there's nothing left in the square root, or the cube root, or any other root, that means there's technically a 1 left over in there. And the square root, or cube root, or fourth root, whichever one you're dealing with, of 1 will always just be 1. So this square root will go away, leaving us with just 7 times 2, which is 14. So I'd like you to take a moment, go ahead and pause the video, and see if you can't try to find the square root of 200. Okay, so just like before, we're going to start with our factor tree. 200, we'll break it up into 2 times 100. And we'll circle the 2. 100 will break up into 10 times 10. Neither of these are prime, so we'll continue. 10 will break up into 2 times 5. 2 and 5 are both prime, so we will circle all 4 of them, which gives us the square root of 200 is the same thing as the square root of 2 times 2 times 2 times 5 times 5. It doesn't matter what order you put them in when multiplying, so I always like to go smallest to largest to keep track of my numbers. But if you're more comfortable putting them in the order that you see them, that's perfectly okay as well. And now from here, for every pair of the same number, we can cancel them on the inside and multiply 1 to the outside. So 2 times 2 will give us a times 2 on the outside. 5 times 5, we can multiply a 5 to the outside. And now this 2 that's by itself in here, there's nothing to cancel it out with, so it has to stay. The square root will stay, leaving us with 5 times 2 is 10 times the square root of 2. So the square root of 200 is the same thing as 10 times the square root of 2. From there, we're going to introduce a few more facts about simplifying roots. These will be a much faster method to go about it. So, the first fact is that the square root of a squared is equal to the absolute value of a. Let's go ahead and see why that is for a moment. If we had just said the square root of a squared is equal to a, meaning no absolute values, then if we wanted to simplify the square root of the quantity of -5 squared, we would end up getting -5, the value that's in the square. But we know that whenever you take the square root of something, you cannot get a negative result. This comes from the graph of the square root function if you were to graph it, you would start at 0, 0 and get something that looks like this. Notice that if you plug in any negative numbers, there is not a y value as a result, meaning you cannot get a negative y as your output, meaning you cannot get a negative answer when you take a square root. So this cannot be possible, which is why we have this absolute value here. The square root of the quantity of negative 5 squared is the absolute value of this negative 5, which gives us positive 5. Now, if we have the cube root of a cubed, remember cube root means for every 3 of the same factor, you can cancel them out and bring 1 to the outside. So for the cube root of a cubed, the result is just a. No absolute value needed. And if you look at the graph of the cube root function, it looks similar to the square root function, but it has a left side. When you plug negative numbers into it, there are y values as a result, which means you can get negative results. So the cube root of negative 3 quantity cubed is negative 3. And in particular, we say that we can apply this to all types of radicals. If n is an even value, then the nth root of a to the nth power is the absolute value of a. And if n is odd, then the nth root of a to the nth power is just a. So these rules, remember them for the square root and cube root, and then just apply that exact same process to anything. The square root has an even radical index, so whenever you see an even radical, know you will need the absolute value, and whenever you see an odd radical, you will not need the absolute value. So, to finish up this video, we are going to simplify the 5th root of negative 243. We need to represent it in one of the 2 formulas that we just mentioned before, dealing with the nth root of a to the nth power, and then simplifying from there. We just have to find a way to rewrite it like that. So the first thing we should do is create a factor tree for 243. 243 can be divided by 3, which gives us 3 and 81, and we'll circle 3. 81 is the same thing as 9 times 9, and we can break up 9 into 3 times 3. So circling all of these, we get the 5th root of negative 243 is the same thing as the 5th root of negative 3 times 3 times 3 times 3 times 3. But we can't quite write this as the 5th root of negative 3 to the 5th yet, because we need that negative to be inside the 5th power. So we can introduce a little trick here. This is going to seem a little bit odd, but it's important to remember how multiplying negatives works. If you multiply 2 negatives together, then the result has to be a positive. So multiplying 2 negatives is the same thing as multiplying 2 positives, which means we can rewrite this problem as the 5th root of this negative 3 times, we're going to change every pair of positive 3's to negative 3's. So we changed these 2 to both negatives because positive 3 times positive 3 is 9. And negative 3 times negative 3 is positive 9 as well. So it doesn't change the problem as long as we work in pairs. So again, this positive 3 and this positive 3 will become negative 3 and negative 3 as well. And now notice what happened here. We've now rewritten the problem as negative 3 times negative 3 times negative 3 times negative 3 times negative 3, which can be now rewritten as negative 3 to the 5th power. And the 5th root of negative 3 to the 5th is just negative 3 because it is an odd exponent. Odd radical index, that really should be said. Okay, so from here, go ahead and take a moment. Try to simplify the negative 6th root of 64. Okay, so now let's try this together. So we're going to take 64 and break it up. We can rewrite 64 as 8 times 8. 8 can be rewritten as 2 times 4. We'll circle each of our 2's. And 4 can be rewritten as 2 times 2. Which gives us 2 times 2 times 2 times 2 times 2 times 2. So we get the negative 6th root of 2 times 2 times 2 times 2 times 2 times 2. There's a lot of 2's here. And now this 6th root tells us that we need to get a 6th power inside of this radical. So we're going to change this to the negative 6th root of 2 to the 6th power. And now our rule before this said the 6th root of 2 to the 6th, because this is an even exponent, even radical index, it can technically be changed to an exponent, which we'll talk about in the second video of this section. But again, this 6 radical index tells us that we are going to change this to the absolute value of what's inside this 6th power, which is 2. And on the outside, we have a negative, which we'll put multiplied to our answer. So we get negative times the absolute value of 2. The absolute value of 2 is just 2. So negative times that 2 gives us negative 2. Notice we got a negative answer. But that's perfectly okay because that negative started on the outside of our problem. It does not affect what's inside the radical. The negative cannot be on the inside when we're dealing with an even radical, but it can be multiplied to the outside.